Hello everyone, Mr. Melham here, and today our goal is to review the Simple Machine Practice exam. The aim of this lesson is not to teach the material from scratch, but rather to support the learning that we've already done in the classroom to help better prepare you for the exam that's to come. So let's begin with this here. I'll start on this page. This is number 2, apparently. This bicycle has 2 pedal gears and 7 wheel gears. The way it is set up right now will make it. Well, let's analyze this picture here. What do we have? We've got a gear on the pedal and we've got a gear on the wheel. So if we look at the gear on the pedal, it is set up on the small gear. And we know small gears are really easy to move. So this person is going to have a really easy time pedaling this bicycle. Now, if we look at the back gear, set up on the big gear, it's set up on the largest one in the back, which means that, well, the wheel's going to move slower. And we know wheels that move slow actually move very forcefully. So let's take a look at our option here. It's easy to pedal and the wheel moves forcefully. So the best option here in this list here, well, easier to pedal, that's right. Harder to pedal, no, that's not right. Great for speed, nah, the wheel is gonna move very slowly. So our answer for this one is gonna be, it's easier to pedal. Let me draw that in. Bam, that's the right answer. Let's move to number 3. So we've got 3 gears here. 3 gears. We can see them in the image. And they're attached to the pedal. That's going to be really important. They're attached to the pedal. Which gear should the chain be set on to make it easiest to pedal? Okay, we know that easiest to pedal means put it on the small gear. So we want to put the chain on the small gear for the pedal. So let's take a look at our options. Yeah, the smallest gear. If we put it on the biggest gear, it's going to be hard to pedal. That's a good thing if you want to go fast because it'll reward you with speed. But it's not good if you want to pedal easy. So let's move on to number 4. We got the following image shows the gears that connect to the back wheel. Okay, this is important. These gears connect to the back wheel, so the wheel of the bike. And it says here, to which gear should a bicycle chain be attached to make the back wheel spin slowly? We want to make the wheel go slow. So what do you want? Put a small gear or a big gear? We want to put it on the big gear. Big gears move slow. So that's the one we need. We need the largest gear. Okay, the smallest gear is going to go really fast. And the medium gear is going to go medium speed. Okay, here we have a picture. We can't really see the back gear. It's not important though. Let's see what it says. The following gears are set up for blank. Let's see here. So we have this front, the pedal is set up on the super large gear. Okay, we don't really need to see the back gear here. We could choose the best option, but I mean, if you do zoom in, you could see, let me get this better in frame. You could see here that the chain isn't on the big gear. It's actually on the tiny gear in the back, which means the wheel's going to spin really fast. And fast wheels are fast bikes. Meanwhile, the pedal right here is on the large gear. The large gears are hard to spin, but they reward you with speed. So we have speed here. It's going to move slow for sure. It's going to move slow and hard, but the back wheel is going to move extremely quickly. So anytime we have this combination, we're creating a lot of speed. On to the next one. What do we have here? We have, which of the following is true regarding the picture below? So what do you have in the picture below? We got a bunch of these gears. Oh, I could see a wheel here. So these are the wheel gears. And I've got the chain set up on the tiny gear here. So yeah, tiny gears move fast. That wheel's going to go fast. This bike's going to go fast. The bike will move fast, but it'll be hard to pedal. That is true. Bikes do not just go fast for nothing. They make you work for that speed. They make you pedal hard. It's going to be hard to pedal, but it'll go fast for you. So this one is true. Let's see the option here. The bike will move fast, but it'll be easy to pedal. No. That never happens. The bike will move slow. Well, clearly these two are wrong options. It's a tiny gear. Tiny gears go fast, not slow. Number 7. So the first elevators that were built, let me move this here. The first elevators that were built used a system of pulleys. This is one of the first elevators ever built. These early designs used fixed pulleys fixed pulleys, okay, that's important to know, that moved the platform up and down. A person pulled down on the rope and the elevator moved up. That's what pulleys do. You pull down on a rope, elevator goes up. The main purpose of the fixed pulleys in the first elevators, okay, you don't have to know anything about elevators. Just what do fixed pulleys do? Fixed pulleys redirect the force. Okay, so instead of having a force move upwards, you change the direction of the force of the rope. So you'll have to pull down to move something up. The forces are opposite. So let's see what the options are here. Changes the direction of the force. First one right there. Does it allow the elevator to move faster? Not necessarily. Pulleys aren't built for speed. They're built, I mean, they could be built for speed, but typically they're built to move things up or down or left and right, depending on how you're designing it. Allow more weight to be moved? Possibly. Give the elevator more power? Not really. It's mainly for the fixed pulleys is to change the direction of the force. So number 8, what do we want here? Marissa wants to make a toy from a heavy cardboard box. She needs to cut the box with a pair of scissors. Which of the following pairs of scissors would require the most effort to use? What does that mean? Okay, the most effort to use. It means which one of them is going to be the hardest to cut. You're going to hold the scissors and you're going to be like, it's so hard to cut with. Okay, what did we learn in class? We learned that things that have long handles are easy, or levers that have long handles are really easy to use. Things that have short handles are really difficult to use. So we want to pick the one that's difficult, the most effort, the one that you have to try the hardest. So it's not going to be these two. These two have really long handles. This has a medium-sized handle, but this one has tiny handles. So it's going to be really frustrating to kind of cut with that. So we want to pick option 4. That's the hardest one. Okay, here we have a similar question. She needs to cut, okay, the end here says, which one requires the least amount of effort? Okay, least effort means it's easiest to use. We want the one that has the longest handle. So this has a long handle. This one has about the same length of a handle. This is a medium size. Okay, so not this one. This is tiny, so this is going to be hard. There's not much difference other than the position of the fulcrum here. You know what? At the grade 4 level, guys, I'm going to be okay if you choose any one of these two here. So we'll go with either of these two. So what do we have here? Randall wanted to set up a lever that would lift the box as high as possible. Which of the following lever setups should he use? All right, so we have this setup. We've got this one. Okay, here we have a long handle. Look how long that handle is. And we have a very short side where the box is on. Here we have the box on a slightly longer arm, but the part we press on is a bit shorter. Here we have a very, very short arm that we're going to press down on. And then this one here is kind of equal on both sides. So let me find something here. One sec. Give me a sec. All right, this is the best thing I could find right now. Guys, check it out. If I put something, let's say I put a box over here, and I put the fulcrum right there, okay? So I have a super long handle, like it goes out super long. If I did this, and I went down like that, see the side where the imaginary box is? Doesn't really go very high. Doesn't really rise very high. Now let's compare that with the opposite. If I put the box, like, on this end still, but I moved the fulcrum to the edge. So I made a very short arm on the other side. Look how much higher it goes. Like it's like not even close. See this? Compare it with this. Barely, right? So we want the box far away from the fulcrum. Move the box super far from the fulcrum so that it actually moves really high up. So let's see which one of these indicates that. I think this one here does a pretty good job. This one, no. This one, no. This one, no. So we're going to go with that. How about this? Where should the fulcrum be placed to make the box feel super light? We want to put the fulcrum as close to the box as possible. So we want the fulcrum right there. That'll make the box feel light. Where should the fulcrum be placed to make the box feel super heavy? Okay, if you want to make the box heavy, move the fulcrum away from the box. Put the fulcrum like right there. That'll make the box extremely heavy. And so number 3 is our option. We have a lady, Alexa, is playing with gears. She notices that for each time she turns gear 1, Gear 2, this one right there, turns only halfway. Gear 2 only turns halfway because it's a bigger gear, so it takes longer to turn. Because Alexa used more force, it has nothing to do with her force. She used less force, nah. It's that the distance around gear 2, in other words, the distance is the perimeter, the distance around it is larger than gear 1. Gear 1 has a very small distance, so it turns a lot quicker. So we are going to choose that one. Okay, it's a bigger gear. Bigger gear has more distance to travel, so it takes longer. Here we have a clothesline used to hang clothes out to dry. It's made up of a simple machine that makes it easier to move the clothes back and forth. So this thing goes back and forth, left and right. Which simple machine is used? Okay, these are, let's see what our options are. Gears, can't be gears. There's no teeth on them. There's no cogs. There's no sprockets. There's nothing. So it's not gears. Lever, no. I don't see a fulcrum. I don't see an arm that rotates around anything. A ramp, no. A ramp is like, oh, why did I put a check mark for ramp? No, we don't want to put check mark for ramp. Let's get rid of that. So a ramp is like a slide, right? It's a slide. You can move things up and down a ramp, right? To make life easy sometimes. And pulley, that's going to be what we need. This is a pulley. It's not an up and down pulley. It's a left and right pulley. Okay, number 15, we have a conveyor belt. We have so this is like at the grocery store where you put your food over here and then the food moves where the arrow is showing to the cashier. And then she takes it and scans it and puts it in the bag for you. So these things here, we got 2 pulleys underneath. Let me skip to the bottom here. Which of the following images shows the direction the conveyor belt will move in? Okay, so the conveyor belt is going like this. How do I know that? Because the arrow, look at the arrow, right? The arrow is going this way, so it's wrapping around. It's going like this, guys, right? So which one of these shows that? This one doesn't. This one starts out good. Look, see this? It starts out good, but then this here shows it's going back the other way. It's not right, so we're going to X this out. This one shows it's going the opposite way. No, we want it to go this way, so this is wrong. This one looks right. Yeah, this is curling and then it continues to curl. This is good. This one's wrong because it's pointing the wrong way. This is the one we need. Okay, we got several items containing levers are shown below. Which of the given levers are second class levers? Okay, second class levers. What does that mean? It means the load is in the middle. The load's in the middle. So here we have the fulcrum in the middle. No good. That's not class 2. Here we could put a nut right there. That would be the load. We have the fulcrum, and then we've got I should write with my pen here. I've got the effort and I've got the fulcrum and effort. Yeah, this would be class 2, nutcracker. Fishing rod, probably not. This is a fulcrum. This is the effort. And then the fishy hanging here. That's my fishy drawing. Fishy. Well, I don't even know what that is, but this is going to be the load. This is class 3, so we're not going to choose that. Wheelbarrow, perfect. Look, we put the rock in here. Effort, fulcrum. Okay, perfect. This is the load is in the middle. This is great. Crowbar is, depending how you use it, it's usually a class 1 lever. Tongs, we have a fulcrum in the middle. No good. Hockey stick, class 3. It's a sporting equipment. This one here, fulcrum, is in the middle. No, this is class 1. And this one is a class 1. The only 2 are wheelbarrow and, let's see here, wheelbarrow, teeter-totter. We're good. Oh, wait, teeter-totter. No. What am I doing here? Somebody was yelling. Somebody was watching this and saying, oh, no, Mr. M, clicked the wrong one. Yeah, you're right. It was nutcracker in wheelbarrow. All right, we're almost halfway through this. Which of these items is an example of a third-class lever? Third-class lever, what does that mean? It means the effort is in the middle. So it's not scissors, that's class 1. It's not the nutcracker, that's class 2. We've established that. Fishing rod, yes, class 3. Well, how do we know that? Because you put your hands right there. This is called the effort. Okay, this is the fulcrum, and the fish is the load. Look what's in the middle, effort. Wheelbarrow, we looked already at it. It's a class 2. Crowbar is a class 1 usually. This is class 1. Fulcrum's in the middle. Hockey stick, class 3. How do we know that? Because look, effort, that's where your hands go. The fulcrum is right there. And then the puck is the load. Look what's in the middle. Perfect. Pliers, class 1. So we don't want class 1s, and this is class 1. So what does that mean? It means we're going to choose the fishing rod and the hockey stick. So we'll click this one here. Key thing to remember about class 3s is that they're involved in sports. So if you see a sporting stick or something, a bat, a stick, a racket, they're always going to be class 3s. They make things go really fast. They're just not really strong at moving things there. Like they couldn't move a brick, but they can move a little tiny puck or a little tiny birdie or a ball. They're weak, but they're fast. In which direction will wheel 1 and 2 spin? Okay, if this wheel spins that way, that must mean the wheel touching it spins the opposite way. Okay, which means the one touching it spins the other way. And then the one touching this one will, so we have 2 touching it. We have this one. And this one down here is also touching it. So it's also going to go that way. Okay, these 2 will match because they're both touching this one. They have to both go the opposite direction. So what is it asking? Which direction will wheel 1 and 2 spin? Okay, this is counterclockwise. This is counterclockwise. Okay, so we'll pick that one. Sometimes kids ask me, how do you know which way is clockwise? Look at a clock. Look at how a clock moves. Okay, clock moves like, kind of like backwards here. So it's like clockwise, counterclockwise, mirror image. Yeah, clockwise, counterclockwise. Number 19, which of the wheels will spin in the same direction as wheel 1? First thing I recommend you do is figure out which way wheel 1 is spinning. So we have wheel 5 spinning to the clockwise direction. So wheel 1 must be going counterclockwise. Wheel 2 must be going clockwise. And then this one is going counter, and this one is going counter. Okay? Because they're both touching a wheel that's going clockwise. So what are they asking? Which one will spin in the same direction as wheel 1? Wheel 1 is going counterclockwise. Which other wheel is going counterclockwise? Not 2, 3, and 4. Both of them are. So we'll say yes. Okay, number 20, we have a person lifting. Basically, which one shows the direction the rope will be pulled in? So when this lady's pulling on the rope, how will the rope be moving? Will the rope be going up? Obviously not, just pulling down. So the rope should be going down. This one shows the rope going up. It's basically she's pulling down on the rope, and the rope says, I'm going to go up, right? Clearly, like, it doesn't make any sense. So we don't do these 2. Now here she's pulling on the rope, and the rope is actually going down, and here she's also doing the same. So it's like they're like this one and this one are both right. If you pay close attention, one of them is actually wrong, because when she pulls down on this, when she's pulling over here, okay, will this side of the rope go down, or will it follow up around? You see where I'm getting at? It will follow up and around. It's going to go up and around. This is the right one. This is wrong. So option 4, that's the one we need. Sailboat. How do we get the sails up? Basically, it's just asking us, how do we get these sails up? Look, if you look closely here, okay, we got, it's hard to see, but it's a pulley system. Okay, anytime you want to move things up and down, I shouldn't say anytime, but most of the time, if things are going up and then down and up and down, you need to get things up, and like say a flag, right? You want to get a flag up, then you want to get a flag down. Or a sail, you want to get up and down. It's always going to be pulleys, almost always. So it's none of these, it's just the pulley. Now, a pulley is a wheel. Yeah, pulleys are wheels for sure. So it's like, oh, should I choose both? No, you have to pick the best answer, okay? So not all wheels are pulleys, right? But all pulleys are wheels. So the better answer is going to be pulley, because some wheels are not pulleys. Don't choose wheel. Wow, that was kind of confusing, but think about it. It'll make sense. Terrence, what's he doing? Okay, so Terrence looks like he wants to get a rock onto the truck. And it says, which of the following statements describes how the lever helps Terrence lift the rock? How does this lever help Terrence lift the rock? How does it help him? How? Well, he's going to push down, and the rock's going to go up. Also, notice that the fulcrum is super close to the rock. Okay, so he's trying to make the rock feel light. So the lever makes it faster. These levers don't make things faster. They just lift things up, right? So we're not going to pick this one. The lever multiplies the force, so Terrence does not need to use as much force to lift it. We just said that, right? Because the fulcrum is so close to the rock's going to feel super light, okay? It's going to multiply his little force over here, little baby force, into a huge force to get that rock up. So we're going to choose, so far the best answer is this one. The lever reduces the friction. No, friction, guys, is when when things are grinding on a surface, when they're moving like this, right? We're not doing that to the rock. We're just lifting it up. There's no friction. The lever changes the direction of the force so that the rock can roll right into the back of the truck. This rock ain't rolling into the truck. He's just lifting it up, and this guy, I guess, will take over. So the best answer here is going to be multiplying the force. It's basically going to make him stronger. Choose the lever in which the fulcrum is located between the load and the effort. So we want the fulcrum, let's see here. We want the fulcrum in between the load and the effort, right? So we want basically the fulcrum in the middle. What do we call levers where the fulcrum's in the middle? We call them class 1 levers. Great. So we've talked about fishing rods. They're class 3. This is a class 2, right? We're not interested in those. Where's the fulcrum here? It's right there, right? That's the fulcrum. That's where it's pivoting. That's where it's going to go. It's going to rotate around this. You're going to put your hand here. This is effort. You're going to smack down here. And the load is going to be the staple that's going to shoot out of this into the paper. Okay, so this is going to be the load in the middle. It's going to come out of this thing. This is a class 2. Why do I have class 1? Oh, that was the one we were talking about, what we're looking for. So this is going to be class 2 lever. We've talked about walnut crackers. This is a class 2. Have we talked about this? We've talked about it in class. This is class 2 lever. This is a class 2 lever because you have the load. It's going to lean on this part. And then you've got the effort of your hands, and the fulcrum is the wheel. So this is class 2. Hockey stick, class 3. Teeter-totter, class 1. Scissors, look at that fulcrum. Look at that effort. Look at that load, the paper. Class 1. So we have to find these two. Okay, so we'll click 7. We'll click 8. But I can't see anything else that's class 1. So we just end it right there. Choose the class 2 levers. Oh, this is simple, right? We just talked about these, right? This is class 2. This is class 2. This is class 2. This is class 2. That's about it. So we'll click, let's see, 2, 3, 5, and 6. 2, 3, 5, 6. That'll get you 2 points. Choose the class 3 levers. Simple, right? Guys, we've got this by now. Look, class 3. So this one's class 2. Stapler like that is class 2. This is class 2, class 2. This is class 3. Great. Class 1, class 1. So what are we going to click here? We're going to click option 1 and option 4. They're both class 3s. Did I miss one? No, just 1 and 4. 1 and 4. Which of the following can be used as a class 1 lever? So a stapler, look, you're going to, depending where you put your hand, these ones here, actually, these little staplers, these normal staplers here, let me zoom into it. They're actually built a little differently here than the one we looked at earlier. You actually don't push on the edge here. You push somewhere like here for effort. And the fulcrum is back there's the fulcrum. And the load is the staple that comes out of here. The load is the staple that comes down. So this is a class 3 lever because the effort's in the middle. Okay, these are not very strong staplers. You could not drive a staple through a thick stack of paper with that staple right here. It doesn't work. You need one of these super powerful, where is it? Class 2s where the load is in the middle and the effort is on the tip and the fulcrum is right here. These are the beasts, right? These are the class 2, the load's in the middle. But as soon as you put the load on the edge and the effort in the middle, it becomes a class 3. It's built for speed. Okay, it's not very strong. We don't care about that. We just want, the question asks us for class 1. Wheelbarrow, we know by now this is a class 2. Teeter-totter is class 1. And a shovel's tricky because you can use a shovel in many ways. If you dig the shovel into the ground, I'm going to do my best drawing of a shovel in the ground. Here's the handle of the shovel. Okay. And then you've got like that. And if you don't remove, if you just put your hands right here and you pull down and the dirt goes up, but you're not lifting it, you're just bending it, then over here, right here where it bends, where it tilts on the earth, that's going to be your fulcrum. They're all the same color. Oh my God, this must look really messy. But effort here, fulcrum, and then the load will be the dirt. So yeah, that's one way to use it. This could work. So we're going to pick shovel and teeter-totter. And option A. Okay, number 7. A lever is a simple machine. Yes, it is. And it multiplies the input force in order to lift a weight. In order to lift the weight shown in the diagram with the least input force, the fulcrum should be placed at point P. So input force is the force you will apply, the force that you will push down with your hand. The one that's going to make it easiest, in other words, the least amount of input force, will be when we put the fulcrum really close to the weight. So option P is going to be it. 28. Where should the fulcrum be placed to make it as difficult as possible to lift the box? So we don't want to make it easy to lift. We want to make it hard. So then move the fulcrum back. Put the fulcrum right there. So if we're pressing down here, move that weight as far away as possible and that box will feel heavy. So we want F. F is it. 29. Patty grouped a number of objects according to the type of lever each contains. Okay. Patty discovered that the scissors did not belong in the third group. Where's the third group? Third group is right there. She's like, scissors didn't belong in here. Well, let's find out why. Fishing rod is a class 3. Okay, we've talked a lot about that. Hockey stick is a class 3. But scissors, they're actually class 1s because the fulcrum is in the center between the effort and the load. So this is a class 1. Okay, so it clearly doesn't belong in this group here. She made a mistake. So what can we establish here? It doesn't belong in the third group because it's smaller than the other levers. No, not necessarily. It doesn't have to be smaller. That's not why it doesn't belong. Have the load in a different place, maybe. Are not a type of sports equipment like the other levers. Well, I guess it's not sporting equipment. So I guess that would kind of be technically right, but is there a better answer? Because the fulcrum is in a different place than the other levers. Yes, the fulcrum is in a different place. In the scissors, it's a class 1. Fulcrum's in the middle. But in the hockey stick and the fishing rod, the fulcrum is on the edge. Completely different setup. So from a science perspective, yeah, I mean, this could be right. And the load isn't sure, but this is the best one from like a science perspective. So we always have to pick the best answer. If group 1 includes only class 1 levers, which means the fulcrum is in the middle, we'll keep that in mind, then which of the levers in that group does not belong? So in group 1, which one doesn't belong in group 1? Okay, tweezers. Yeah. Okay, so why tweezers? Let's see here. Let me open up a tab. Let's see tweezers. So tweezers look like this. Should I buy it? No, I'm not going to buy this. Let's zoom into it. So with tweezers, what do we have here? We have a fulcrum. Okay, that's where it's connected, where it's going to rotate around and pivot. Here we put our effort, okay, right there. And we pick things up with this. This is the load, effort, fulcrum. It's a class 3 lever. That's the one that doesn't belong. Okay, pry bar is a crowbar. That's a class 1. Teeter-totter, class 1. Tweezers is the one that doesn't belong. 2 gears are put together so that their cogs mesh together. What does mesh mean? It means they connect. They mesh. The cogs mesh together. That's what gears do. They mesh these cogs together. If the driver gear is turned in a clockwise direction, then the drive gear will, okay, where's the drive gear? Driver gear, okay, that's the one we're going to spin. The drive gear will go the opposite way. Counterclockwise. Counterclockwise. The given figure shows 4 different gear setups, 1, 2, 3, 4. Which 2 gear systems change the angle of motion? The angle of motion, okay? So in other words, the gears are pointing in different directions, right? Up, down, left, they're different. Okay, this one they're pointed in different direction. This one they're actually pointed together. This is like facing the same way. These ones are facing different directions. These ones are interesting look. They're facing the same direction. So not this one. So we're going to pick 1 and 3. There it is. The gear train shows a small gear between 2 large gears. The smaller gear in the middle is called an idler gear. I even labeled it here. The main function of the idler gear is to, okay, function means what's its job. The function of the idler gear is to increase the speed of the follower. No, it doesn't increase speed of anything. The idler gear may go fast, but its job is not to make this go fast. Actually, it slows down after that. Change the direction of motion of the third gear. Yes, because if this turns this way, then this goes that way, and it changes this direction to this way. Now, without the idler gear, if I just connected this and this together, then this big one and this over here are going to go in opposite directions. But because the idler gear is in between them, it forces their directions to match by changing the direction of that one. Turns all the gears counterclockwise. No, that's not what it does. Decrease the amount of force. No, it has nothing to do with forces. It's about all about directions. 34. Show the direction that the rack moves in. If the pinion is turned in the clockwise direction. So we want to turn the pinion this way. Since this is connected to it, it's going to go the opposite way. Okay, pinion's not going to move. Okay, pinion's going to stay right there. It's going to rotate this way, and it's going to push this to the left. So we want to pick this. Now, if I flip the direction, if I made the pinion go the other way, then the rack will go to the right. Okay, so they're going opposite directions. Which of the following gear systems will assist the car in steering left and right? So here's how a car works. You have a steering wheel connected to a rod, connected to this pinion, which connects to a rack. And as the pinion spins, the rack will go left and right, pushing the wheels left and right. So it's a rack and pinion. Which of the following gear systems operates in 2 different planes of motion? Click all the answers that apply. So 2 different planes means 2 different directions. These are both facing the same way, so nope. We want 2 different directions. These are both facing the same way, so nope. Okay, this one's interesting. Here we have around motion, rotational motion, and here we have linear motion, right? So this one goes in a circle and this one goes in a straight line. 2 different types of motion. That's one option. Look at this one. This one is vertical and the other one is horizontal. 2 different motions. That's good. This one, they're all facing the same way, so no. And this one, they're all facing the same way, so no. So we're going to pick 3 and 5. 3 and 5. There's a lot of reading here, but I'm going to skip it to the bottom. What is the advantage to having the driver gear being large and the follower gear being small? Okay, we learned that if you have a big driver gear, it's going to be hard to turn it. It's going to turn really slow, but the small follower gear is going to go, it's going to go like really, really fast. That's the advantage. You're going to create speed. You're going to turn the big one really slow, but your reward is the other one's going to turn really, really fast. So we're going to pick the follower gear goes very fast. The driving gear will go fast? No, it can't because it says it's a giant driver gear. So big gears don't go fast. The driving gear will take less force. Quite the opposite. Big gears are actually harder to turn. So it'll take more force. The follower gear will move with great force. That's not true because the small gear will go fast, but because it's a small gear, it's going to be really weak. It's not going to move very forcefully. It's a small gear. Small gears go fast, but they're weak. So not this one. Okay, so we have a guy named Raj. What does he want to do? He wants to make the follower gear spin really, really fast. Gear 1 is going to be the driver. Gear 1 is the driving gear. Which one of them shows what he uses? Okay, he wants to create speed. Gear 1 is the driver. Oh, but look at gear 2, the follower. It's super big. That's not going to be fast. That's going to be super slow. Gear 1 is big. Gear 2 is small. This could work. This one will not work. Here's the third one. Gear 1 and 2, they're both the same size. You're not going to get any speed out of that advantage. Here they're both big, so they're both going to move really slow. The best one is going to be option 2. Here we have wheels and axles. Okay. She placed them so they're going to touch each other. She turned the first wheel so that it spun in the clockwise direction. We can see that here. Which of the following illustration shows how the other wheels will turn? Okay, let's analyze this. This goes clockwise. This goes counterclockwise. This goes clockwise. This goes counterclockwise. Let's see which one of them matches with that. So we want an under arrow like this. Not this one. Clearly, look at this arrow. Not this one. Look at that arrow. Oh, wait. I messed up. I got tricked by my own question. Oh my God, that's embarrassing. This arrow. Let's see. So I drew it wrong up here. Okay. This is not right because this is actually turning in the same direction as this one. Look, if I keep following this, it's going to go clockwise. It's still going. This is also clockwise. That's incorrect. Let's erase this and do it again. So this is going to go this way, opposite, like that. Okay. And this one's going to go opposite of that one. It's going to go like this. And then this one will go like that. That's better. Okay, let's analyze this. This could work. Oh, but what's that arrow here? Look at really closely. Look at that in here. What's that thing going left? Going to the right, I mean. What is that? No. A little bit of a... Oh, look, we have another one there. No, what is that? No. This whole thing wrong. So it's going to probably... Oh, look, we got another one. What is this? Let me see this one. Okay, this one looks appropriate. Look, clockwise, counterclockwise, clockwise, counterclockwise. Okay, this is it. That's why it's important to check your answers always. Even Mr. Melham makes mistakes. Got to check it, but I catch him most of the time. So Wade set up a conveyor belt. He moved boxes. I skipped sentences here, guys, just because I feel like I know what these are. Let's look at the important thing. He knew that the roller at position 2, here's the roller at position 2, will turn in the same direction as the roller in position 1. Will it? Will these two turn in the same direction? Let's see. This will turn this way because of the arrow, and then it'll come back and turn this way. Okay, well, let's see here. This is clockwise, and this is also clockwise. Yeah, so far so good. Let's see the rest. Move the boxes one at a time. If you put the boxes one at a time, it'll move them one at a time. Otherwise, it doesn't really know. If you put all the boxes together, it'll move them all together. It's not going to say, okay, you box go first, and the second box. No, it doesn't do that. So no, it doesn't do this. Turn in the opposite direction of roller at 1. So will this go in the opposite way? It won't. Anytime you take 2 wheels and separate them, or 2 gears and separate them, and hook them by a chain, both gears or both wheels or rollers will turn in the same direction all the time, not in the opposite direction. Move back and forth. No, they don't go back and forth. Back and forth. No, they're locked in place. So that's the best one, top one. Gear 1's the driver gear. Which of the following statements about the given gear system is true? So here we have the driver gear right there. Gear 2 will turn faster than gear 1. Will 2 turn faster than 1? 2 small. Small goes faster. 1 is big. Big goes slower. So no, it's not this. Gear 3, here's gear 3. Oh, gear 3 is small. Will turn faster than gear 1 and gear 2. So will this turn faster than this and that? Yeah, it will. It's the smallest one. Small ones win in speed. It will take more effort to turn gear 2 than gear 1. No, it'll actually take more effort to turn gear 1 because it's bigger. It will take more effort to turn gear 3. No, it won't. Gear 3 is small. Small gears are easy to turn. Won't take much effort for that. So we have our answer right there. Okay, we have a guy. Okay, let me summarize this here. He's got 3 gears. Okay, 1 gear will hook up to the motor. 1 gear will hook up as an idler gear. And 1 gear will hook up to the axle. The point of the idler gear is to make sure the motor gear and the axle gear turn in the same direction. You need that. You need the motor and the axle to move together so the car moves forward. So what's happening here? What does he want here? Which of the following combinations should Jared choose to get his car to move the fastest? Okay, the fastest means, which one of these is going to be the driver? Let's think about it. The driver is going to be the motor gear. The motor gear is going to be the driver. The driver is the motor. So we want the motor to be big and the axle of the car, where the wheels are going to turn, to be small, because the small axle gear is going to turn the axle really fast if it's small. And then the wheels will turn really fast too. So we want to have a big motor gear and a small axle gear if we want the car to go fast. Here the motor gear is small, no good. Look, big motor gear, tiny axle gear, winner. Okay, now same problem, but which of the following is going to be the best to get his car to go uphill? Okay, for uphill, we don't need a fast wheel. We need a slow wheel, because when the wheels are moving really slow, because of the gear setup, they actually move strong. So what we need here is we need a very small motor gear and a very large axle gear. It's like bikes, right? On a bike, you want to keep the pedal, if you're going uphill, you want the pedal on the smallest gear, the pedal where your legs are moving, right? You want it on the small gear, but you want the wheel on the back to be on the largest gear. Same here. We want the motor to be on the small and the axle to be on the big one. That's going to make it go uphill like nicely. Okay, now same problem here, but now he wants to make sure he doesn't want his motor to work too hard. Okay, he wants his motor to relax. He doesn't want his motor to be like, oh, this is really hard to move. So what should he choose? Should he choose a giant gear for the motor? Should he? Really? No. Why? Because if the motor has the giant gears are like, oh, it's so hard to move. The motor's going to stress out. We want the motor to have the smallest gear. This is the one. This is going to be very relaxing for the motor. Okay, so we want this one here. 6 kilogram bucket of rocks with a fixed pulley. It's a fixed pulley. He then lifts the same bucket of rocks with a movable pulley. We know the movable pulley will make it feel lighter. The fixed pulley will keep it feeling 6 kilograms. The movable pulley will cut the weight in half. John noticed that when he lifted the bucket of rocks with a fixed pulley, the bucket took more force to lift. Yeah, it did. Took more force to lift than the movable pulley. It sure did. Took less force to lift? No, it's a fixed pulley. Took the same amount? No, not at all. All right, so did not require any force to lift. No, you need some force to lift. Took the same amount of force to lift as the movable pulley. No, movable pulley will take less force. Okay, took less force to lift. This one here. Yeah, so the first one's right. Can opener uses which of the following simple machines? Can guys look at it? Look. Teeth, right? On a wheel. Teeth on a wheel. Gears. So we're going to pick gears. Okay, what do we have here? Basically 3 gears facing the same direction. They're not bevel gears. Bevel gears face different directions. And they make like a 90-degree angle, like an L shape. Nothing like that here. Spur gears is so far good. Crown gears, haven't looked at crown gears. We haven't even looked at that. Worm gears, no, they look different. Rack and pinion, that's for cars, and they look different. Yeah, spur gears. 48. The given figure shows a simple pulley system that can lift the given weight by rotating the wheels. Simple. That's how pulleys work, right? Wheels rotate. The two wheels are marked 1 and 2. If the pull is released, wheel. Okay, so we're holding this here. We're holding this, but then we're gonna let go. What's gonna happen? What's gonna happen? Okay. Wheel 2 will move up. If I pull this, if I let go of this, this weight is going to fall down and it's going to pull this pulley with it. So this can't be right. Wheel 1 will move down. That can't happen either. This is a fixed pulley. It's fixed because it's locked in one spot. It's not going to fall. So it can't be this. Wheel 2 will go clockwise. Wheel 1 will go clockwise. Okay, let's see here. If I let go of this rope is going to slide to the right and spin the wheel to the right, or in this case, clockwise. This rope here will spin. So let's see here. As this thing is falling down, it's going to spin to the left. Just imagine this. Imagine how this works here. It's falling down. The rope is going this way. It's going to spin so look, we have these arrows set up. Clockwise, counterclockwise. 2 will go clockwise. Nope. No, look at 2. It's going counterclockwise. Yes, that's the one. See that? Perfect. 49. In a system of gears, the gear that has force applied to it is called the driver. That's what that's the definition term of it. Here we got another pulley. He built the pulley system. If the weight has a mass of 200, this has 200 grams. That's how much it weighs, 200 grams. Then how much force will be needed to pull the string with to move the weight up? Since we have a movable pulley right here, it's a movable pulley hooked onto the weight, movable pulley, then it's going to take half as much force. So you only need to pull half of 200 grams. 100 grams is going to be the answer. There it is. How much rope will Jason need to lift how much rope will Jason need to lift the following weight 4 centimeters up? So we want to lift this 4 centimeters up. Now, normally you just need 4 centimeters of rope to pull with to make it go up 4 centimeters, except in a movable pulley, it punishes you. Why does it punish you? Because it makes the load feel lighter. It's rewarding you with saying, hey, I'm going to make your life easier. I'm going to make the weight feel half as heavy for you. But I'm going to punish you by making you pull 2 times more rope. Fair trade, I say. But that means we need 8 centimeters of rope. We need double rope. If the weight below has a mass of 200 grams, then how much force will be needed to lift it up? Here, what is this? What kind of pulley is this? It's a fixed pulley. It does not change the weight. Everything stays the same. 200 grams will be 200 grams of pull to get that thing moving. How much rope will you need to pull in order to lift the weight below this weight 10 centimeters high off the table? Since it's a fixed pulley, there's no punishment. There's no punitive measures here. If you want to lift it 10 centimeters, you just need to pull 10 centimeters of rope. The thing will go up 10 centimeters. That's all you need here. Okay, it's only the movable pulleys that will give you consequences. Guys, this was a longer video, but I hope it was a lot of help. I know you guys have a test coming up in a couple days, and I just wanted to do a little bit to make your life a little bit easier. Guys, if you have any questions, drop a comment in the comment section below or send me an email. Send it to me, put it on Google Classroom, my personal email, whatever. Love you all. Catch you next time. See you later. Bye-bye.